So, how can a ring modulator sound anything like a triode gain stage from a vacuum tube? Well, a ring modulator is a kind of four-quadrant multiplier. And a four-quadrant multiplier takes two inputs, a carrier and a modulator, and it produces an output that is the product of those two input signals. So the fact that I have a circuit that can multiply two voltages to produce a third is key here. Okay, now why is multiplication important? That's because for a triode, when I apply a voltage to the grid, the output that comes out of the plate can be expressed in terms of a quadratic equation. So the idea that I've been chasing is using the four-quadrant multiplier just as that, as a means to multiply voltages in order to solve or get the result of that quadratic. Here's how I expect this can work. Amplification means more than just an amplitude change. I could also have a DC offset where the input wave is just given a positive or a negative DC offset with respect to the ground or center. It can also do things like wave shaping, where the top half of the wave, its magnitude may change more than the lower half of the wave. There's other effects in the leading edge of the curve might be amplified different than the falling edge. So there's all kinds of different behaviors in wave shaping that are more interesting. For trying to mimic the behavior of a triode, I'm less interested in the amplitude change in the DC offset. I'm more curious about the wave shaping. So starting with my triode equation for the grid voltage versus the plate voltage, if I take out terms that deal with the DC offset, like C0, and I factor out amplitude changes like C2, my leading term here, what I can do is focus on a simplified version of the equation, which looks more like this, where the plate voltage is the product of the grid voltage times the grid voltage plus a constant. And in doing some modeling and some testing in Excel, just doing the simplified equation, it tracks really well. It actually looks a lot like our main equation that we started off with. And this comes from this simplified form here. So now, how does that translate into a schematic? So our original ring modulator schematic took two signals and through this processing resulted in a product of the two input signals. Now we made some changes to it and we put in these log amplifiers on the input, and that led to a better output. So in trying to produce an output similar to a triode, I have my two signals here, the grid voltage plus a constant times the grid voltage. So really all I should have to do is change these inputs. So I've got the signal multiplied times the signal plus what I'm calling the grid bias. And that should give me a product of the grid times the grid plus that bias voltage. Taking that out of the tripod. So, can you see that at all? 1 kilohertz sine wave. He's going in. It's going through all of that nonsense. I am measuring the output. That's coming into the yellow channel. The green channel, that's my input. And here we are on the scope. So, green signal again, that's my 2.2 volts peak to peak, and the output is ridiculously pegged. I'm turning the DC down, that's ground, gradually going up, gradually still. All right, so there's something there. Well, it's not working as I would have expected. If I keep turning that up, basically pegs it and it goes into a square wave. All right. I don't know. I'm going to have to take a closer look at what's going on in here. Not out of the woods yet. So I think the problem with that is essentially the A and B terms in my equation are essentially the same. And if I go back to this equation that the ring modulator is based off, this A minus B term essentially goes to 0. Actually, I have a very, very tiny grid bias DC voltage in there, so it's really not doing anything on that half of the curve, and that's that squared off wave that we saw. It was this A plus B squared term giving me the dog ears kind of curve. So I think what I'm going to do is redo this as an A plus B squared to do a grid voltage plus grid bias squared, and that simplifies the circuit a great deal. What it winds up doing is half of my circuit goes away. This entire A minus B branch goes away. So I have this half ring modulator, or a two-quadrant multiplier. So I just have my signal coming in here, and I'm going to add the bias on this non-inverting input. And then I'll have my squarer circuit here to give me A plus bias squared. So let's give that a try. I'm also going to try this both with and without the log function, just to see how the circuit behaves. All right, so this is looking at what is going on in this half ring modulator circuit. So this is my 220 hertz input signal, and you can kind of see that I've got my output is inverted with respect to the input signal. It's definitely more pointed at the bottom half of the signal, and I do have this flattening going on at the top half of the signal, but it is badly distorted. Now, what will happen when I put the log amplifier in there ahead of this? Hopefully this might smooth some of that out, and we might get something approximating a sine wave back again. Okay, so now my input is going to the log amplifier. You can see that it's much more squared off. It's like it's being compressed, and it doesn't look as much like a sine wave again. Now, I'm better behaved in this lower portion of the output signal, but the output itself it looks like it's gotten squared off. Okay, so that's my DC offset. So the offset is about 0 at this point, which means each one of these peaks for the sine wave input, that is going through the diode. It's pushing its way through. If it's positive, it's going through the anti-log and it's getting inverted. If it is negative, it's going through the anti-log, but it's getting inverted again. So now I've got this sort of shark tooth pattern. So a negative offset, I'm out of phase. Positive offset, I'm in phase. And it's very, very slight. When they're equal, back to my shark tooth, this frequency is twice my input. It's distorted and it looks kind of cool, but it is an octave up. All right, interesting circuit, but not at all like a vacuum tube. I know what you're thinking. What does this sound like with a guitar running through it? And will I get an octave up? Let's find out.
A few moments later.
You can kind of hear an octave in the note. Oh, definitely hear the octave. Another thing I want to try is a variation on this two-quadrant multiplier. I'm going to go back and put the bias in as an input in the inverting input. I am going to increase the gain on this initial stage. I'm putting in 100K here, so this has a gain factor of about 10. It's going to go through this same squarer circuit to give me my A plus bias squared. I'm also going to play around with putting the log circuit at the output stage rather than the input to see what difference that makes. All right, over at the oscilloscope. So you can see my input waveform coming in here. This is 220 hertz. It is going through my half ring modulator, so it's going through the two diode pairs. And I do see a form of this inverted sombrero shape where it's more flat at the top and more pronounced at the bottom. But notice that my frequency is doubled. This is to be expected from a ring modulator. When a signal modulates itself, it does double the frequency. In a roundabout way, or actually in an extremely direct way, I've got my even harmonic addition here. Now I'm squaring this, and as it passes through zero, this gets squared, so it turns positive again until it crosses, and then it's positive and it gets squared. So that's what these humps are. Now, since it's going through the log amplifier on the last step, this is really nice and compressed sounding, so it makes an octave fuzz. All right, so let's take a listen to it, listening with the guitar.
A few moments later.
You can definitely hear the octave action in those real high notes like that. All right. Has a sense of like ripping paper. It also does not like chords. It's like there's way too much harmonic information. Right, usable effect, if not very glitchy.
24 hours later.
Just to prove it to myself that this would actually work, I went back and I expanded the range that the bias could reach. And let me check what I have this set on. All right, I am at minus 0.598 volts. For this setting, and this is the pattern that I had expected to see, trying to mimic the triode output, where my output should be inverted and it should be pointing down when the input signal is in the uppermost position. So I've got that, and I have this flattening at the top. But what's cool, if I start to change that bias, I get these side lobes that kind of appear. And if I set it right there in the middle, I can get that octave effect again. Let me see what that is. So that is it's floating around. It looks like DC 0.1. So a positive 1/10 of a volt. And if I keep going, I'm going to guess that this is about positive 1/2 a volt. 0.608. So now I'm in phase, and I've got what I call the inverted sombrero. Listen to what happens to the output as I sweep past this. All right, let's try that with a guitar signal. All right, so I've got the guitar plugged in. So it sounds pretty mellow. I can't say it would sound like a tube, but it doesn't sound bad. There is a tendency, if I overload it too much, it gets really ratty really fast. All right, I'm going to knock it off of bias here, and so what am I going to do? I'm going to put this in the more negative direction. So if I bias it more positive or negative, I'm back to the fuzz territory. Which isn't a bad thing. Overall, I have to declare this as a successful experiment. I was able to get a variant of a ring modulator in a two-quadrant multiplier configuration to produce some even harmonics or use it as a fuzz octave. It turns out that this is a pretty versatile circuit. Now, is it perfect for emulating a triode? Probably not in this state. I've had some comments from viewers about how log and anti-log amplifiers will maximize their output really fast and they'll distort quickly. So I've also had people recommend using Gilbert cells as a multiplier, and that would probably work better. But, what I'm really interested in at this point is, I obviously kept referring back to Spirit in the Sky because that is such a unique fuzz sound. And when I was playing around with a ring modulator, it just popped out. And I kept thinking, maybe I'm on to something there. Maybe there's something to this octave fuzz circuit that was part of Greenbaum's original Telecaster that had the fuzz pedal built into it. Maybe he had some octave fuzz action going on in there. I don't know. I hope you have enjoyed all of this. I left a lot of the discovery in playing around with the circuit, doing the different experiments. If you're into this kind of stuff and you want to find out more of these kind of experimental circuits, I'm probably going to dive into fuzz pedals next, because that little gem of an idea of I might be close to the spirit in the sky fuzz sound, that seems kind of irresistible. Thanks for coming along. I appreciate it. And I will see you in the next video. Catch you there.